Hey guys, welcome back to Algebra 2. Today we are going to cover 7.2 properties of exponential functions. Let's get started. So graphing exponential functions. So we're going to expand on this a little bit. It was introduced yesterday. We're going to expand a little bit more. We are going to be using characteristics that we've used in quadratics, polynomials, square root function, absolute value function. We're going to be using these characteristics and applying it to exponential functions. So we have graphing y equals a times b to the x power, okay? We know that our parent function is y equals b to the x power. So if it says, what is the graph of y equals negative 1/3 times 3 to the x power, we're comparing it to the graph of the parent function. So for this, our parent function would be y equals 3 to the x power. Okay, so what's different between y to the 3x power and y to the negative 1/3 times 3 to the x power is that negative and then the 1/3. Two different things that affect our graph. So first we need to look at our parent function is over here in red. Y equals 3 raised to the x power. Okay, your y-intercept is at 0, 1. So this is our parent function. So what happens with our new transformation is we have a negative and we have a 1/3. So if we plug in points, -2, -1, 0, 1, 2, these are our inputs, these are our outputs, and if you look, B is our transformation. Okay, so some things that you notice is one, it's reflected across the x-axis. Okay, the reason why is because of this negative. Okay, another thing is these numbers are smaller, they're crunched, okay? So they're more compounded, and that is because of our 1/3, okay? So that A we've seen that A variable, how it affects other graphs. So it's the same thing. If it's a negative, it's reflected across the x-axis. And in this case, it is between 0 and 1, so our numbers are more compacted, and it grows, or in this case, it goes down slower. Okay, so let's look at a more general, broad overview that we can look at for our graph, okay? And we'll talk about our h and our k and how that affects the graph. So first thing, we have our parent function of y equals b to the x power. Okay, so some transformations are first, let's talk about a. So like on the previous one, we had a times b to the x power. The a affects it. If a is greater than 1, it's going to be stretched. It's going to grow or decrease at a faster rate. Okay, so it's a stretch. If a is between 0 and 1, it's more compressed. Okay, and so that is a compression. And then if a is a negative, or if there's a negative out front, then we know it's going to be reflected across the x-axis, or in layman's terms, just flipped, okay? And then translations horizontally and vertically. We know that h is horizontal and k is vertical. We talked about this. So in this case where you're gonna see them, we have our x minus h plus k. We've seen h, we've seen k. H moves it left and right, and we know if you look here, it's in parentheses. It's always opposite of what you think. So if h is negative, it moves to the right. And if h is positive, it moves to the left. Okay? Or this is h. And then if k is positive, it moves up. And if k is negative, it moves down. Same thing that we've talked about in previous chapters. So now we're going to apply it to exponential functions. So let's look at another example. So we have translating the parent function y equals b to the x power. So anything that's added on from that is a translation. So how does the graph of each function compare to the parent function? So here we have y equals 2 and then x minus 4. Your parent function is y equals 2x, and our translation is the 2 and then the x minus 4, okay? What is different is this minus 4 up in parentheses, okay? That is a h, so that's a horizontal transformation left and right. It's a -4, so all we need to know is since it's a negative, it moves to the right 4. So our parent function function is in red. And then here's your xy values. Here's xy values for the parent function. And then all we need to do is this is just move 4 to the right, okay? So our parent function is red. Our transformation is 4 units to the right, and that's it. So let's look at some more examples without graphs. So we have y equals 4 into the x plus 2. Okay, so our parent function is y equals 4x. Now we have y equals 4x plus 2. Okay, x plus 2 is in parentheses, that's your h. It's a positive, so it's opposite. This moves left 2 units, okay? And what can we do to check it? Desmos. So I pulled them up here. So we have y equals 4x is our parent function, our red. And then y, or 4 to the x plus 2 is 4 units, or 2 units to the left. Okay, so if you can see, the transformation is left 2 units. And you can always pull it up in Desmos to check your answer. Okay, here we have y equals 5 times 0.25x plus 5. Okay, so this is kind of one we haven't seen before in this section. This b, 0.25, is between 0 and 1, so we should know this is a decay. Okay, this is an exponential decay. So our parent function is y equals 0.25x. So it's just a decay, exponential decay. So our 5 is our a. It's greater than 1, so this is a stretch by 5. Okay, 0.25 to the x power, we said that's a decay. And then the plus 5 is on the outside, that's our k, so this means it is translated up 5 units. So let's check it. So we have this Desmos. Okay, it's a decay, and our red was 0.25. And then here we have stretched up 5. It's kind of hard to see, but it is stretched up 5 units, or it's, you know, more stretched out, and then it is up 5 units. Okay, and then that would be our graph there. Okay, now let's talk about continuous compounded interest. Okay, so this PERT or PERT, you're going to see that a lot, and it's a lot to deal with finance. It's where your interest rate is just compounded continually with your principal or your initial amount that you put into the account, and it's a continuous interest rate that just keeps compounding continuously, okay? Kind of in the definition. But this is a super easy formula to remember, because PERT or PERT, you're gonna hear that a lot, especially like, you know, in statistics or like bigger financial classes or in the real world, but PERT is compounded continuously. So let's look at an example. Well, let me go over this again. Your P is your principal. The principal is your initial amount that you put into the bank or you put into your account. E is just our mathematical number that we're going to use. Interest rate annually. So this is your interest rate per annually. That is compounded every year. That is in your exponent, and that's being multiplied by the time in years that the money is in that account. Okay, so let's look at an example. So suppose you won a contest at the start of 5th grade and you deposited $3,000 into that account that pays 5% annual interest compounded continuously. So every year it has an interest rate of 5%. How much will you have at the account when you enter in high school 4 years later? Please express it to the nearest dollar. So what we're gonna do is we have A equals P times E raised to the RT, so PERT. So our principal, or our amount that we start out with that we put in is $3,000. So that is going to be your P, and then E raised to the 0.05. So you got to change this to a decimal, move it 2 places to the left, so 0.05 times T, which is the time that is in the account, which is 4 years in this case. We're going to round it to the nearest dollars. So hold on real quick. Let me see if I can do it. We need to get our scientific calculator, okay? So we said it was $3,000. Okay, so here's Desmos, $3,000. We don't see E here, so we have to go to function. And it's right here. E raised to the, I guess I could have done that one. E raised to the, so the rate or the interest rate was 0.05. So in parentheses, I'm going to say 0.05 times 4 years, close, and we get 3,664, and it said round it to the nearest whole dollar, so it'd be $3,664. So we put in $3,000. The interest rate was 5% each year, and that's so after 4 years in our account, we would have $3,664. Okay, pretty cool, right? So we get 3,664. Watch in MathXL, it may say round to the nearest like cent. So then in this case, it would be like $3,664.21. So just watch for rounding what they want you to do. Okay, now it says, how about how much will be in the account after 4 years of high school? Okay, so we put it in, we put $3,000 in. After 4 years was when we were entering in high school, okay? And then it's asking how much after 4 years of high school, so an additional 4 years. So be careful here because our time isn't 4. Our time here is, if we put it in 5th grade and at the end of high school, that would be 8 years, okay? So 3,000 is again how much we put in times E, and then our interest rate is continuous. It's the same, it's 0.05, but our time here is 8. So after 8 years, how much do we have? So let's go to our calculator. We have 3,000 E, and then instead of a 4 here, I'm gonna delete it, and I'm gonna say after 8 years. That's for 5th grade to after graduate, that would be 8 years. So after 8 years, we have $4,475. Okay, so we have $4,775, right? I think, yeah. Okay, and that's it. That's it for 7.2. So MathXL, you guys have 6 total questions. So let us know if you have any questions.